We'll just wait a couple more minutes and then we'll begin. So while we do wait for a few more people to join, I'll just go through some housekeeping rules. You will see that upon entry, you have been muted by myself. This is just so we can keep a consistent flow throughout the webinar. At any point, if you have a question, pop it in the chat box and I'll come to it at the end, or alternatively, I will unlock the mic at the end of the session so we can have an open discussion. This is being recorded and it will be put on social media, the website, or if you would like a copy, please email me at ashleighm@scioninstruments.com and I'm more than happy to share with you both the recording and the presentation itself. So today's webinar is about utilizing every aspect of the diode array detector and how we can use it to look at impurity profiling. I will go through the brief overview of the HPLC SCION 6000 if it is new to you, or just a refresher for those of you who are familiar with it. We do have full presentations on all modules, including specifications and demonstrated analysis. If that's something you would like to be sent, again, please email me and I'm happy to share those with you. So in our HPLC lineup, it is a modular system. It gives you complete flexibility and to configure it how you want to configure it. So at the top, we have the 6510 Organiser. This is the solvent cabinet, so it houses all of your mobile phases. And it also contains the communications board. The next, we have the 6100 pump. We have two types of autosamplers depending upon your requirements. So we have the 6210, which is a standard autosampler, or we have the 6220, which is the autosampler with Peltier-based heating and cooling. We do have a column oven that is the 6310, and that again is Peltier heating. And currently we have a choice of 4 detectors. That is the diode array, the UV, fluorescence, and the RI. So if we have a quick view of each module. So our solvent cabinet is an extra large solvent cabinet. It can hold 6 1-litre bottles as well as 3 500ml bottles. So it makes it so much easier that you don't have to be continuously changing mobile phases. You can secure them within the organiser so they're ready to transfer over when you need them. As you can see at the back of the organiser, there is a leak detector, and just behind this panel here, there is also a drain. So if there was a leak, before it even reached the leak detector, the design of this column oven would be to drain it away. As I've said, it contains the communications board for the whole of the HPLC, so the organiser is a mandatory part. It does contain the comms board as standard, so you don't need to order it separately. So when we talk about HPLC, the most critical module is the pump. So the SCION 6100 is a quaternary pump and is a 600 bar pressure limit. The pump is used to move the mobile phase and sample throughout the HPLC. We do supply the pump as a standard basic isocratic quaternary pump. However, we do have the option to upgrade the unit and have a degasser installed and also a low pressure gradient unit. So the degasser will remove any dissolved air from the mobile phase, ensuring that the system can run smoothly and there'll be no pressure fluctuations or flow rate problems. If any air does get into the system, this can cause restriction of the mobile phase flowing through the LC, and this will lead to not only pressure issues but also chromatography problems. So the low pressure gradient unit allows a method to be ran under gradient profile, and that means we can have up to 4 different mobile phases with different solvent ratios. So without the low pressure gradient unit, we can only run it in isocratic mode. So that means we can only have one mobile phase from a single bottle with the same 100% profile across the board. There's many benefits of having a low pressure gradient unit, and it is usually for method optimization, making a run quicker, separating complex compounds that a standard isocratic run can't achieve. So although the degasser and the low pressure gradient unit are optional, we always recommend using the degasser unit regardless of how many mobile phases you're going to have, as this will keep the system running smoothly. When changing between mobile phases, or if you do have air in the system, it is a manual purge valve. It can be controlled through specialist maintenance software or also through Compass CDS, which will enable the changeover of mobile phase to be done quickly, meaning there's less downtime. So if we look inside of the pump module itself, so as you can see, this is the 6-channel degasser. We have 2 spaces for Autosampler wash, and then the remaining 4 is what provides up to the 4 different mobile phases. Here we have the low pressure gradient unit, which gives us the option again for that gradient profile. When you purchase the low pressure gradient unit, it will come with the mixer. As you can see, this system, it hasn't actually been used, it's just been installed. So you don't need to order a conventional mixer separately. If you want to change to a semi-micro volume mixer, that would be an additional upgrade, but as standard, the mixer does come with the low pressure gradient unit. As you can see, it's a manual purge valve, and we also have the option for a plunger wash. However, this system didn't have it fitted. So a plunger wash is always recommended if you are running a normal phase type application where the solvents are very volatile and can cause the plunger to stick, but also if you are using reverse phase mode and have a buffered solution, especially with a salt, the plunger wash will stop the salts from building up and causing issues with the pump. So if we just have a brief look at the benefits of the 6100 pump, it does have superior retention time stability and excellent gradient reproducibility, and this is because we have something called the HFM mode. So the high frequency mode means that when using a gradient program, we will double switch the proportional valve to ensure that the amount of gradient you've requested is actually applied to the column and it's not lost in the tubing. So as I said, it is a 600 bar pump, and this allows us to have faster flow rates, which will reduce retention time. So overall, it'll increase productivity without compromising on the chromatography. We do have options for low volume degassing, and this will reduce the purge time and also reduce solvent consumption. So in this slide, it shows the example of the superior retention time stability, which usually requires a column oven to achieve. However, in this example, there was no column oven. So as you know, in HPLC, retention time stability is vital, as peak identification is based upon comparing the known retention time of a compound to an unknown under the same analytical conditions. So if our retention times changed and drifted, then it's very easy to have misidentification of compounds and peaks could be missed altogether. If the retention time shifts too much, then the run's not going to be long enough to detect all peaks. So retention time stability is critical. On the right, you can see a very basic diagram of how the high frequency mode works, and it's in the solvent delivery system. So in low frequency mode, the two solvents are delivered independently and then mixed. But during the high frequency mode, the two solvents are delivered already pre-mixed and ensured that there's consistent composition delivered throughout the whole system. So what will happen is there's one stroke of the proportioning valve which mixes and then delivers the pump through the system. Switching between these different solvent ratios during a gradient run is faster, allowing the gradient to be applied to the column, ensuring that you've got proper separation and it's not affected by a wrong gradient profile. So as I've said, we do have two autosamplers. In our range, we have the 6210 or the 6220. The only difference between the two is that the 6220 is thermostat controlled. This is critical in toxicology and pharmaceutical laboratories, where sample integrity is even more critical. Both have excellent precision, and that's through the high precision syringe drive that we have. It has minimal dwell volume, and it has an automated needle wash method to protect carryover, to make sure that there isn't any carryover. The ultra-low carryover of less than 0.003%. It does have very sensitive leak sensor checks, so if there is a leak in the system, this will be quickly reported back to you through Compass. The system will stop and you'll be able to identify the leak quickly. So it is a high sample capacity. We have, as standard, it is a 202 ml vial tray. However, this can be upgraded to either 128 sample 4 ml vials or 384 or 96 well microplate capacity. Here we have a look at the injection volume precision over 0.5 microliter injections to 50. So this was 10 injections of the same volume. And you can see it even at 0.5 microliters, it was only 1.25% RSD. However, 20 microliters is typical for modern day HPLC methods, and the precision variance was less than 0.3%. If you are a low throughput laboratory or you maybe don't have the budget for an autosampler, then we do have a manual injector. It is the Rheodyne 7725i. This is a highly stable manual injector, and it's a continuous flow between the load and the inject position. It is an automated stop-start function. It's got built-in positioning and it connects directly to our organiser. So as soon as you inject your sample in that inject position, the Compass will acquire the run and your data will be collected immediately. As standard, it is a 20 microliter sample loop that comes fitted, but if you see on our price list and on our spares and consumables, you can order different size sample loops for this. It's not restrictive. So we have our column oven, which is Peltier-based heating and cooling. It can house up to 3 25 centimeter columns at any one time. We always recommend using a column oven, especially in gradient program methods, because it does provide additional retention time stability, and also it can actually improve chromatography. So what it does is using a column oven will lower the viscosity of the mobile phase, and it will allow it to pass through the system at a lower pressure, and it does give better separation. So as I've said, I'm not going to go into detail about every detector in the portfolio. This is primarily based around the purity data processing. So I'll just quickly go through the diode array before we look at actual data. So the diode array is a standard HPLC detector that is used to detect the presence and the purity of any sample compounds. It utilizes an ultraviolet range and a visible light range via the deuterium and tungsten lamp, but it is also fitted with a mercury lamp so we can do automated wavelength checks. So as the majority of compounds absorb light at a specific wavelength, the way the diode array works is it will monitor the changing of intensity at which the compound absorbs light and the time in which the change occurs. These are converted from a signal and output as the chromatogram. So the diode array can monitor a wide wavelength range of 190 to 900 nm, and it is a very versatile detector for detecting both unknown compounds and compounds what you know the target wavelength range for. So unlike the UV detector, we can actually monitor 4 wavelengths at the same time. So we can monitor the whole set from 190 to 900, then 4 specific absorbances as well. So the benefit of using the diode array is the fact that we do get a 3-dimensional chromatogram too. So this contains the usual time and response of your sample, but also the third component, which is the wavelength at which the maximum light was absorbed. It is using this 3D data that allows us to be able to identify peak purity. As well as the peak purity, this 3D data is used in spectral data analysis, which is part of the purity calculations. So I'll discuss that in a few slides. So this chromatogram shows you what a typical chromatogram looks like when you look at a sample containing numerous compounds using the multi-wavelength method within COMPASS. So the main diode array range was 200 to 650, but then we did have the target 4 compounds at 254, 480, 530 and 620. So as you can see, we do have 6 compounds present, and all compounds were visible at both 254 and 530, but you can see that the peak area varied for all of them. We did know what the target analytes were, so by monitoring at these 4 target wavelengths, we were able to successfully separate and quantify all target compounds without any method modification or running numerous methods. This is not possible using a UV detector. So if we look at a bit of the specification, we do have full specification sheets, but overall the diode array gives high resolution results with very low drift. The variable air fan design reduces temperature variations, which can cause issues when using the 3-dimensional data. In addition to that, if you do need that extra bit of sensitivity and want an overall better spectra, we can offer a thermostat controlled flow cell. As I've said, it is a wide range detector from 190 to 900. So in order to not only control the LC, but to do the peak purity processing, we have to use COMPASS CDS. So for those of you who don't know, this is the SCION Instruments chromatography data system. It is used to run all of our GC, but also we have the capability to run other instrumentation. So it has powerful integration, calibration and reporting tools, and it is 21 CFR compliant. To support your application, we do sell a wide range of HPLC columns. The most popular are your standard C18 or C8 phasers, but we do have modified phasers for special applications. If you have a particular column that you're interested in, please drop me an email and I'm more than happy to help. Or if you're not sure what column you need for your application, just let me know. So if we look at the diode array features that enable us to do the 3D modeling and the peak purity processing. So in conventional HPLC, we have an acquisition of a single chromatogram monitored at maybe 1 or 2 wavelengths. However, this can include many unresolved peaks that are not visible just looking at the 2D chromatogram. So adding that third dimension to the chromatogram, which is the wavelength, we can do more data handling of complex samples, and it's very information rich. So sometimes it's called 3D modeling, sometimes it's called peak purity, other times it's called 3D data. This is all interchangeable. So we can look at the optimal wavelength. If we have run a sample over a range, because we're not sure, we can use this 3D data to look at the optimal wavelength, and this is also used as part of the peak purity process. The library search is also critical for peak identification, and it just adds that extra level of security that you're confident in the results you're reporting. Both of these are combined to give the peak purity. So within Compass, it is the real-time data that we can view during the acquisition. And the good thing about using Compass CDS is that all the data is stored within a single data file. I know on other software platforms, you do have separate data files for both the 3D and the 2D data. So what we need to remember is that the 3D plot of a spectra for a compound is like our fingerprints. It will be different for each compound analysed, but it is method specific. So why is peak impurity important? So pure compounds will absorb light across a predefined range and will show identical spectral profiles each time the compound is analysed under the same method. So impure compounds will be identified as possibly having a similar spectra, but only for sections across the width of the peak. So if we look at a peak and it's not obvious to the naked eye that it's coeluting, when we do the peak purity, that will split the peak into sections and look for any differences across the spectra. What is important to know that when looking at peak purity or spectral comparisons, it is a qualitative assessment only. If you want to confirm what the impurity is, then you would need to do further investigation through using known reference standards or comparing in other spectral libraries. So the peak purity is critical in the pharmaceutical industry, as this will identify any impurities during the manufacturing of the product or even in the method development and validation. So this leads to improved processes in the pharmaceutical industry. So the algorithm behind the peak purity is always designed to confirm the presence of one or more impurities by comparing those spectral data slices. So what will happen is multiple slices are taken at the apex, the upslope and the downslope sections of the peak. What the software is really looking for is a mismatch between those spectral data slices. So showing the peaks not fully resolved and there's one or more coeluting peaks present, which we will call the impurity. So realistically, we should be saying it is an impurity analysis, because we're not trying to determine if something is pure, we're trying to determine if something's coeluting and we're not actually seeing it. So with any method development, we should always do peak purity first to be sure that the results we are seeing are not, that there's not other compounds being masked by the main compound in that sample. If we neglect to do peak purity, then it means any hidden impurities that we can't see could falsify the results. And in method validation, this is one of the key criteria for a lot of validated labs, that peak purity is used as a check. So if we look at how we determine the peak purity, so when we do it, it is just for the diode array detector due to this 3D data that we can obtain. So what we will do is the software will begin by comparing the peak spectra. If the peak is pure, then all the visible UV spectra in that peak is identical to a reference standard that we have stored in the database. When a peak is determined as pure, then in the quantitative analysis that follows, we are confirming that any amplitude differences is due to a change in concentration and not just due to an interfering coeluting peak. However, when we see significant deviations in the spectra obtained, this is an indication that there is an impurity. So as I've just said, and this diagram shows, we will focus on the upslope, the apex, and the downslope of a peak. The good thing about Compass is that we also have a noise absorbance threshold, and this allows us to identify any baseline impurities that will be otherwise overlooked or completely missed. So when we talk about upslope, apex, and downslope, the number of spectra that we choose across this range will affect the results. So in Compass CDS, we do have the option of just the apex only, so it will take the central point of the peak. You can have 3, which is the upslope, apex, downslope. 7 spectra, which is 7 cross sections between the upslope and the downslope, or all spectra, which will split the peak up from the absorbance threshold of the upslope to the baseline of the downslope. So in addition to choosing how many number of spectra you want to compare, you can also choose at what % of the peak height you want to look at. So on the left is you'll see the sigma method. This is how it's predefined in Compass, and the percentage of the peak height is where it will take the measurement. So the larger the sigma number, so either sigma 5 or sigma 5%, the more accurate the calculation is. And this is because the lowest point of your peak height is the most sensitive to asymmetry. So this will be able to help with identifying any hidden impurities that are otherwise lost in the baseline. So this is the example of how we can look at the peak purity using the different functions within Compass. So this is the same data file, just processed using 3 different peak purity methods. So the first method, we just used the apex only. And as you can see, it just takes the small spectral slice right from down the middle. And this shows that it is completely pure. And in that section of the spectra, there's nothing interfering. When we look at the 3 spectra, it takes the upslope, apex, downslope. You can see the red line at the upslope is an impure compound. So what it's doing is it's found that the spectra expected to see at that front upslope based off the reference standards stored in the system doesn't match, so there's an impurity. If we go to the downslope, it's only yellow, so this shows that although it's similar, there is a cross-section of those splices that are similar. There is some that don't match. So although we can't determine it's impure, we can categorically say that it's not pure. When we take the all spectra, so each part of that peak has been sliced, you will see that the amount of medium and impure area on the graph is more significant. So we've gone from apex only that was completely pure to a more defined in the all spectra. So it really depends on what you are focusing on. If you're not bothered about what's at the baseline, you just want to confirm that the main peak is indeed what it is and there's no impurities behind at the same peak height as the apex, then you can just choose the apex. So when it comes to reporting the purity results, there's many different ways you can do it. So when we look at this, it doesn't give us any quantitative numbers. It just gives us an idea of where the purities and impurities lie. So what we can do is we can customize Compass that will include not only the colored peak from before, but numerical results in a table. The table can be generated in the main results just by using the report properties function. But again, it depends upon the purity calculation you've selected, whether it's Apex, 3, 7 or all. We will also talk about in a few slides how spectral comparisons and the 3D model display can be used to enhance the purity results. So the results table, you have many different options dependent upon what segment of that peak you were looking at. So if I was just going to put the pure apex, again, it would just take the middle. But the most three popular choices is the area impure, the pure and the medium. This will highlight the percentage of how much of that sample is impure, pure or similar spectra. So during many method development and validation, the criteria for that will be 90% of the sample, the compound analyzed must be pure. So although they're not, some companies aren't particularly bothered at what point the peak is pure or impure, it is the total area percentage. And this is how it looks for our peak. You can see what I've done is I've included the per apex, which is just taken the splice right down the middle, and it is at 1,000, which correlates with the graph we seen originally. There is 90.78% pure compound as reflected in the green area of it, the graph. The medium was 5.5%. So what that's telling us is although there's something impure, it is structurally similar to caffeine that's given the same spectra, similar spectra. And then we've got the upslope and the downslope tail ends, which are completely impure, and it does not match with the spectra from the caffeine. Another way that we can visualize the peak purity is looking at the ratio chromatogram. So in the ratio chromatogram, this is fully automated during the peak purity processing. And what it will do, it will plot the absorbance ratios of two pre-selected wavelengths over time. If the ratio doesn't change over that time, then the peak is deemed pure and definitely only contains one compound. If the ratio changes, the peak is deemed to contain two or more compounds or impurities. So if you see at the bottom, this is exactly the same peak as before with the all spectra selected. So where the purity value is 1,000 up at the top, you can see that my ratio line is flat. It's at 1, so it's steady, it's not changing. So this section from just before 0.5 to just after 0.9 is what's pure, and that correlates to what we're seeing down here. However, at the beginning of the upslope and the downslope, you can see the line has changed. As the ratio is fluctuating, that is also telling us that it is not pure. This just gives another indicator that there are impurities within the peak. If you didn't want to view the graph here, because it doesn't really show much, you can just export this ratio chromatogram as well. So this is the whole basis of the peak purity program. So when we do use the diode array detector, it is this data viewing window that we'll see. This is the same sample as before. As you can see in the top left window, this is your standard 2D chromatogram. Your top right, this is the 3D modeled map that shows you the intensity of light absorbed from time and the wavelength at which that happened. The bottom left is an interactive window which also shows the absorbance intensity, and we can use this to extract the target wavelength for a compound which we didn't previously know. We also use this window to extract the spectra that will be part of the peak purity and spectral library match, and that's what's shown in this window. So at first glance, this peak looks absolutely perfect. It's symmetrical. It doesn't look like there's any hidden peaks. But when we move over to here and we look at the actual mapping, the 3D mapping, we can see that in this section, something has been responsive at approximately, this will be 200, so approximately 220, something is responding at exactly the same retention time as our caffeine peak, which is here. So if we take a look at this map, as you can see here, the dark red intensity is the central apex of the caffeine, and that correlates at 273, which is our target compound for caffeine. We know that its absorbance is 273. If we scroll down to 220, you can see the start of a second compound. So using this alongside the peak purity mapping we've done confirms that the caffeine in our sample isn't fully resolved from whatever this peak is. But as it's qualitative, this information will not tell us what the secondary peak is. We would need to do further investigation. So on top of all that, we can actually build the spectral libraries into Compass. And what we would do is in that window that I've previously just shown you, so in this window here, we will select the apex of the peak and we'd look at the target wavelength here, which is 271. So what we can do is we can add it to a custom built spectral library, and that enables any future samples that we run, we'll be able to compare it, not only display the results, but it'll be used in the peak purity too. What's important here when we add a spectrum to the library is that we give it a description, we add the solvent, the column used, and also the mobile phase. As you can see here, this was just isocratic. If you do use a gradient program, I recommend adding the gradient program either to the spectrum description or the mobile phase box, as for successful comparisons and peak purity to be calculated, you do need matching methods. You need to have run it on the same method to ensure that you get this same spectral profile. So when searching for a spectrum in the library, again, it's the same principle, but instead of creating a library, you will go to the apex and you will search the library. So what it will do, it'll automate this for you and just bring it up in a second window. As long as you have a spectra stored in Compass that is previously been ran, it will show you, yes, this is 100% match. So as you can see here, this is out of 1,000. So 1,000 equivalents to 100%. This is our caffeine standard that I ran in July, and this is a sample from today. It was unknown. It gives me the retention time, but it also shows me the retention time from when I ran it in July. If I didn't have that initial standard in there, these are the results we would get. It would only plot the unknown spectrum and it'd say no matching results because it's got nothing to compare it to. You've got two ways of viewing the spectra. You can overlay it or you can have it separate. When it is 100% match, you wouldn't be able to see any difference. It'd just be perfectly overlaid. So I prefer to leave it separate when it is a good match. If it was a lower match, maybe 990 or 900, I would overlay to see if I could find out at what point of the spectra wasn't matching, and that could also identify which an impurity which is behind, causing the spectra to be not quite right. So all of this information that we've gathered, the 3D mapping, the 2D chromatogram, the 3D chromatogram, and the physical spectra, all of this can be put on a custom report. So with only one click of a button, you can export the results with all of this data on. If you don't do the analysis very often, or if you have a new lab tech that comes in and wants to do a run using the diode array, the good thing about the spectral library is we can actually go in, we can choose our target compound, and we can find out not only what method was ran to obtain this spectra, but the acquisition date, and most importantly, what data file it was taken from. So this allows us to easily go back and even compare new data with the stored spectrum data. We can import or export libraries through an ASCII file. So if you've got more instruments you're adding to the lab, or you've got older instruments and you're upgrading, we can import and export libraries, so you're not going to lose all of that information. So just to conclude, the diode array is a highly versatile detection technique for HPLC analysis. It is very underrated and people don't appreciate how much information we can actually get from the diode array. So although it's great that it can show us a 2D chromatogram with 4 wavelengths monitored, which eliminates method development or method modification, it is this 3D data, the model data, that gives us the most value. So through the spectral library comparisons, we can calculate peak purity and identify any hidden impurities that were previously not visible just off the 2D data. As I've said, it is critical in method validation and in validated labs that this is part of their procedure. But always remember, if we do identify any impurities, we must confirm analysis via the use of other reference standards, as it won't give you confirmation of exactly what that impurity is. Thank you. What I'm going to do is I'm going to stop sharing for now. I will unmute everybody. If anybody would like to say anything, I'll go to the chat box because I can see there's a few chat. How many samples in the autosampler? So the autosampler can have 200 2 ml vials, 128 4 ml vials, or also 3 microwell plates. That is for both the 6210 and the 6220 autosampler. What is the minimum percentage for composition in the low pressure gradient unit? Let me check that because I'm not sure. I have used it in 5% increments, but that's just what I've used it at. I can double check for you what the actual limit is. Sorry, just bear with me. So we can have it in 1% steps. So to get the pure, medium, and impure information, you do need to have a library so it knows what to compare against. Otherwise, it's got nothing to compare to. You don't have to make the libraries in advance. You can run a reference standard and make the library as soon as the data has been acquired. Otherwise, when you compare spectra, you've got nothing to compare it against. Does anybody else have any questions? As I've said, I will provide a recording of this session. It'll be put online, and I'll also send you all a saved version of the PowerPoint for you to go through if you need to. Thank you very much for your time, and hopefully we'll see you on future webinars. Thank you.